So hello everyone. So my name is Nicolas Biev. I'm part of the product-centric ads team at Meta. And today I'm going to present Shopper, which is our framework to leverage sequence modeling for e-commerce ads ranking. So this project is a collaboration with multiple people, and the corresponding author is Amit Jaspal. So today, first, I'm going to set up some context about the whole space of sequence learning, and second, the problem that we are trying to solve. Then I'm going to talk about our framework, Shopper, and finally, I'm going to show some results and conclude with some next steps. So, what is product-centric advertising? So, at, at Meta, we have a product called dynamic ads. So, dynamic ads are like a highly personalized ads where product shown in the ads are actually selected from an advertiser catalog by a multi-stage and multi-objective ranking system. So to give an example on the right, so advertisers will have like thousands or even millions of products in their catalog, and then we trust us to decide which product to show in the funnel carousel based on different signals like click probability, conversions, but also some quality sanity check. So Meta PCA team own all of these models, and the idea is that we have to rank all of these items under very tight latency. And the key that we realize to harness the most gains from this system is to be able to efficiently model a user shopping journey. So what is sequence learning? So um, there's been a pretty drastic shift in the last couple of years for how recommender systems will leverage user shopping history. So historically, user shopping history tend to be like summarized into some like point-wise features. Like for instance, how many purchases they make on average uh, in the last X number of days. However, the user shopping journey can actually be represented by a sequence of event where we could track what kind of product the user saw in the past, what kind of products they started to purchase, but maybe didn't finish to purchase. And all of these events will be tracked over time. So given this sequential nature of the data, one key uh, um, one key factor that we're trying to harness now is how do we aggregate all this event and using in particular some like event encoder or like some summarization layer to have a better signals to fit to our ranking models. However, sequence learning faces three key bottlenecks. So first is a temporal stripping. So most of the time when we consider sequence learning, we actually consider the raw sequence of item IDs. However, we tend to forget to enrich this sequence with context, such as what is the page type used, what is the action that was done. So we used to like strip away this key element that are crucial to help to learn from the sequence learning. Then the semantic sparsity. So in particular in the space of e-commerce, the cardinality of the IDs is huge, and our catalog will like, keep changing. And this make it very hard for generalization because it is hard to learn the joint representation of the different IDs in a given time. And finally, the uh, target agnostic. So when we develop usually architectures to summarize sequence learning into some like meaningful embeddings or signals for the model, this is not done jointly with the actual product that you're trying to rank. These are like standalone process, and we believe that there is also some like loose of opportunities in not doing so. So our framework should then aim to address all of these three bottlenecks. So SHOPA stands for Semantic, Historical, Order Aware, and Product Condition Pooled for e-commerce recommendations. This is a sequence modeling framework that restructures how user journey are defined, contextualized and evaluated against target item. But the key innovation here is basically that we were able to optimize um, the computation of the system by separating uh, offline compute, request server compute, and connected compute. This was a way basically for us to cache and optimize our operations. So I'm going to deep dive into the three components that you are seeing here in the next couple of slides, but at a very high level. In high level, first, we're going to have some offline pipeline, which are going to leverage some foundation models to help us to have very powerful semantic IDs. Semantic IDs are embeddings that are going to be leveraged for the rest of our training. Then we have a part about how do we enrich our sequence and then learn the most efficient embeddings for this sequence. And finally, we have the target-aware attention, will help us to have to leverage the target product during this whole process. So the first part of our contribution is about the enriched event representation. So here an event will be represented by multiple metadata. So for a given product ID, we're going to have an action, a click, impression, purchase, a page, where did the click happen? Was it Facebook, Instagram, on Reels, etc. And then more metadata, in particular time-related metadata, for instance, the dwell time or the recency of the event. And finally, we can also add more product metadata to this concept. So here our approach to learn the best representation of this event is to use two paths. So first, the textual temporal path, where basically every field of the event is embedded and then just projected using a classical MLP. Second, we use a foundation model to do what we do, we call a semantic path, where basically with this foundation model, will help us to have very powerful embeddings for the different ID, in particular a product ID. And then we learn a sigmoid gate that fuses both these two embeddings, and this will help us to learn when to use either one of these two, based on whether the ID signals are already rich or if we need to amplify the signals. Second, we have an order-aware local intent modeling. So acute shopping intent appears as like short burst of related actions and not isolated clicks. So we then therefore use like a 1D convolution over the enriched token to capture the local pattern. So based on some research, we find that the window of size was optimal. And we also have a learnable seed vector attends over the provisional sequence to produce the global intent vector R. So all of this is request level, meaning this will be like only we can do this only with like the user information. Second, we have a product condition pooling. So basically here we summarizing history before seeing the candidate averages away the evidence that matter. So here we want to make sure that we have the candidate as well as part of our learning. So first step, we'll do some conditioning killing. So Mix is a way to also like be able to prioritize the main part of the information. And second, we do some cross attention. So here the target acts as like the query and summarizes the conditioned sequence into a vector. The target does not like just rewrite the vector, you will also help to shape part of the history. So, and finally, we have then the final scoring basically where we have like our like DCN, THE, and style model. And basically we feed all of this information to the final predictions. And we usually track normalized entropy as the main success metric for our model. So another thing I want to stress again is this serving optimization. So here we have three different spaces. where we do the operations. So the offline, where our foundation model is, and we can update the embeddings and semantic IDs on a daily basis. Second, the request level. So at one uh, uh, um, request level, um, for the user, we can already pre-compute all of the enriched sequence and the representation of the sequence already. And finally, for each candidate, we have to do the target aware attention. So our framework, compared our framework to other event aggregation framework, and we were able to have like about a 0.33% any gain, any reduction compared to the PMAR, which is one of the reference that we used. Also a lot internally. We also did some like ablation study to understand exactly where will the gain come from. So our first part of the gain was definitely the enrichment, with like 0.05 coming from just context and 0.02 coming from temporal features. The 1D convolution intent help us to have another 0.05% any on top of that. Yes. Another part we check is really the importance of the foundation model. So by removing the foundation models, the performance dropped by like 0.08%. Yeah, we tested this framework online and saw a very significant gain in our top line business metric with a 0.4% without major p-net latency regression. Yeah. So in conclusion, uh, so there are of course some like limitations to this framework. So first, the embedding stainless. So we have only like a daily update of these embeddings due to our upstream foundation models. Then also we have fixed sequence length. So this is right now a hard limit in our design. And finally, we don't have yet an optimal approach for cold start. Yes, so this is the part of the direction we want to work also in the future. So for instance, how do we do like incremental embedding update or adaptive sequence lengths? Okay, thanks a lot for your attention, and for any questions, please reach out. Please don't hesitate to reach out to the corresponding author.